Professor H. of IIT Madras. This is the live problem solving session for the week 7 of the course. I am Mayank Goyal. I am a research scholar in the Department of Electrical Engineering, IIT Bombay. This course is being taught by Professor S. Shankaran, who is an associate professor in the Department of Metallurgical and Material Engineering, IIT Madras. The course plan for this week is fundamentals of X-ray scattering, Bragg's law derivation, and the factors affecting the intensity. This live tutorial session is happening every Sunday 6 p.m. to 8 p.m. at this Google Meet link that you have joined. So first I will be showing you some overview of the topics of this week. So what are X-rays? So X-rays are electromagnetic radiation which fall in the range of around 100 angstroms to 0.01 angstroms. So why they are special? So they are special because they fall in a specific wavelength range, that is ideal for crystallography. So the, so the so your crystal planes, they have a spacing of around 1 angstrom, and in the range of angstroms, their spacing in the range of angstroms. And the fundamental rule is that you cannot resolve any structure feature that is smaller than probing wavelength lambda. So you cannot. So if you have a large wavelength like visible light or ultraviolet, you won't be able to use that to identify your crystal structures. For that, you need to go for wavelength that is in the range of angstroms or below, and X-rays fall perfectly in that range. That is why X-rays are used to see crystal structures. Now, how are X-rays generated? X-rays are generated by by rapid deceleration of high kinetic energy electrons. So you have a cathode here, which is made of elements like tungsten, and you have an anode here, which is your target material. And by application of voltage across your cathode and anode, you 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 eject electrons, and these electrons fall on a target material cathode anode, and there they decelerate very rapidly. But 99% of that deceleration kinetic energy is converted into heat. So it heats the target material, it heats it, the surrounding X-ray tube and everything. So we need a continuous cooling supply to keep this tube cool, keep the material cool, and less than 1% of it is successfully converted into X-rays, and that also is that emitted X-rays are also divided into two parts: continuous spectrum and characteristic spectrum. So a typical X-ray spectrum contains both continuous curves and characteristic fields. So the continuous curves are the smooth base curves that represent white radiation or heterochromatic radiation. So they fall across a range of wavelengths. And then you have a characteristic spectrum that are very sharp high intensity spikes that are superimposed on your continuous spectrum, and they have special names such as K alpha, K beta, L alpha. So the continuous spectrum is a direct result of electron deceleration. It is also called Bremsstrahlung, which means breaking radiation. So what happens is when electrons hit your material, they deflect and decelerate at different rates, and that emits a diverse range of wavelengths. And when an electron is stopped in a single direct impact, it yields the maximum energy photons, which, or you can say the minimum wavelength photons, and the for which is given by your well-known formula EV equals to h nu max. So 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 this is the limit of wavelength. So it's called short wavelength limit, which is a minimum wavelength, which is given by your C by nu max or hc by ev. And by putting the values for hc and e, you will get lambda swl equals to 12,400 divided by v, where your lambda is in angstroms and v is your applied voltage. Now your continuous spectrum intensity is controlled by your applied voltage. So and it also applied voltage is also controlling your limit of your spectrum, which we just saw, and it is also controlling your intensity, which is the number of emitted photons. So your intensity of continuous spectrum is given as A I Z V per m, where A is your proportionality constant and m is approximately equal to 2. So it is so the total emitted X-ray energy per second corresponds to the area under the curve. So you will have a curve here, and if you integrate the area, you will be able to get the total X-ray energy per second. So, and you can see here the intensity is dependent on both your applied voltage, your atomic number, as well as your beam current, as well as current of incident electrons. And once you cross a specific critical excitation voltage, that is a a minimum voltage that is able to create wavelengths smaller than the characteristic wavelengths, you are able to see these sharp characteristic peaks, which are k alpha, k beta. So for molybdenum, the wavelengths are as k alpha 1 is 0.709 angstrom, k alpha 2 is 0.744 angstrom, k beta 1 is 0.632 angstrom. And unlike continuous wave, characteristic wavelengths are fixed constants for a specific target material. So raising the voltage above the critical threshold increases the peak intensity, but it does not shift the wavelengths. And only highly penetrating K lines are primarily utilized in normal X-ray diffraction work, and other lines are not normally used. So how these characteristics X-rays originate? They originate from transitions from electron shells. So what can happen is your incident electrons can come and knock out electrons from your internal shells, and that creates a vacuum in the internal shell, and that is vacuum is fulfilled by electron transition from higher shells, and that transition gives out a characteristic X-ray with which has an energy precisely equal to the difference between the two shell energies. So your K alpha is formed when an L shell electron fills a K shell hole. K beta is formed when an M shell electron fills a K shell hole. And K shell excitation requires massive critical voltage because it sits closest to the nucleus, so it is the most difficult to knock out. So it requires the maximum. And then we have this called Moseley's relation, which gives us the characteristic frequency, which is directly correlated to the atomic number. So the formula is your lambda square root of mu equals to c z minus sigma, where your c and sigma are constants. So you can see as you increase your atomic number, your frequency will increase. That means your wavelength of characteristic length will decrease. But it does not mean that if you go heavier atoms, you will go smaller wavelengths. So, for example, the L alpha 1 line of heavy tungsten is in the similar range as your K alpha lines of lighter elements like molybdenum and copper. And so that is because L alpha 1 has a has a lower energy, generally has lower energy than K alpha, but due to the very high high atomic number of tungsten, it 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 is able to fall in this same range. So this relation is true only for a particular characteristic like K alpha 1 line. Now we talk about absorption. So so when X-rays encounter matter, they are either transmitted or absorbed. The fractional decrease in intensity is proportional to the distance traveled, and it is given by the linear absorption coefficient mu, which is given as minus d by I or mu dx. So we can calculate the wavelength intensity exiting the material compared to the incident intensity as Ix equals to I naught e power minus mu by rho into rho x, where mu is your linear linear absorption coefficient, and when divided by density, it gives us the mass absorption coefficient mu by rho, and and this remains constant independent of whether the target material is solid, liquid, or gas. And if you have a if you have a mixture or a chemical compound, then it will then this mass absorption coefficient is simply the weighted average of each individual element. And if you so the relationship mu by of mass absorption coefficient is typically follows k lambda cube c cube, but at the absorption edge, that is at the point where the atom is absorbed, where it it absorbs to emit. There's a sharp drop, like for copper it occurs at 1.5. It occurs precisely at critical energy required to physically eject an electron from target K shell. So you can see here that it is directly proportional to lambda. So for hard X-rays which are shorter wavelengths like less than 1 angstrom, they will have a smaller mass absorption coefficient, which means they are absorbed less and hence they are highly penetrating. Whereas longer wavelengths, that is soft X-rays above 1 angstrom, they are easily absorbed because they have a higher mass absorption coefficient. And if you go for very high elements like lead, they have a they have multiple multi-edge profiles because they have because they are heavier, so they are able to absorb different types of edges, different type of electrons. So the K edge requires massive energy, that is, it requires extremely small wavelengths to dislodge inner electrons. So then you have LL shells, which are at higher wavelengths, which correspond to transitions in subshells away from nucleus. Then you have another another effect called Auger effect, where the characteristic emitted X-ray goes goes and hits an goes and hits an external shell electron and gets absorbed and results in emission of electron from the external shell, so which results in further loss of that X-ray intensity. So 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 your yet net yield is number of atoms that emit K radiation divided by number of atoms with K shell vacancy. So this further reduces your yield of characteristic X-rays. So X-rays propagate as transverse waves, where the direction of oscillation and direction of propagation are mutually perpendicular, and the wavelength and frequency determine the periodic cycle, where lambda is given as c by mu, and the phase angle tracks the wave's exact position through its cycle. So at so phi, it is given as phi equals to 2 pi y by lambda, where y is your position across the wave, and lambda is your wavelength. So this explains phase shift, where your so since X-rays are sinusoidal periodic, we can represent them trigonometrically such that we can say A equals to wave is wave equal wave intensity is a sine 2 pi mu t, and if at a different point it will be sine 2 pi mu t minus y1 by lambda, and it can then be represented in Euler's form as Euler's formula A e power 2 pi iota mu t minus y1 by lambda. So when an incident X-ray hits a certain point, it will scatter all across the region, and hence it will result in it will result in a formula such that E equals to sigma n e k e power 2 pi iota mu k minus y k by lambda, where k is your point at different points, each and every point, and then you can take mu t out, so you will be left with e power 2 pi iota mu t summation n ek e power minus 2 pi iota yk by lambda, and then you can divide it in real components and imaginary components using Euler's relationship. So this is the formula for raw wave, but the for detection we use intensity, which is the sum of which is the product of a wave and its conjugate. So that gives us a formula E dash equals to summation Ek cos 2 pi yk by lambda square plus Ek sin 2 pi yk by lambda square. And this formula will help us in understanding the Bragg's law and the difference in intensities we get for different scatterings. So when a wave scatters, it can take different paths to reach from point A to point B, and that difference in paths leads to different in phases, and that path difference can then cause interference, and that can result in constructive interference where if path difference is zero, the net amplitude is maximized, and if the path difference is opposite, then the amplitudes cancel out and the net intensity is zero. So when X-rays fall on a crystal lattice, they reflect, and in normal light optics, we take the surface normal. In X-ray, we use the crystal plane instead of a surface because X-rays interact with the crystal lattice and not the morphology of the substrate. So you have two rays that hit your sample and then emit, and if the path difference is zero, so they are perfectly in phase and at contribution. So they give out the maximum intensity. And what happens is they can one ray can emit from plane A, another can emit from plane B, and that plane B gives us an extra path length, and the difference between planes is given as d dash. So that extra path length is calculated using trigonometry, and the total path difference extra paths traveled is comes out to be around 2d dash sine theta. Now if we want to have constructive interference, we want the part difference to be equal to lambda or a multiple of lambda. Hence we get the equation n lambda equals to 2d dash sine theta. Here n is your order of reflection, lambda is your incident wavelength, theta is your angle of incidence, and d dash is your interplanar spacing. So there are three distinct modes of scattering. One is monatomic gas. So in gas there is no crystal structure. So atoms are arranged randomly, and scattering is done in all directions, and it is also very weak. So intensity will just simply add, since there is no proper path of the waves in perfect. Then you have perfect crystals. So there, if they satisfy Bragg's law, so that periodic it has periodic arrangement, and very few directions meet the strict condition of Bragg's law. So scattering is high, and since it's a perfect crystal, scattering is highly focused and strong. So we are able to have interference, and if it satisfies Bragg law, then amplitudes add. If if it does not fall in that particular condition, then the emitted rays will be out of phase, and they will cancel each other out, which will result in zero scattering. So experimentally, in an X-ray diffractometer in laboratory setting, so you have your angle of incidence theta and your angle of reflection theta. So your transmitted beam will be at an angle of 2 theta from your incident beam. So in X-ray diffractometers, we measured this 2 theta value instead of just theta. Hence, X-ray diffraction plots are in plotted as 2 theta. So mathematical constraints of diffraction are, so by definition sine function cannot exceed 1. So n lambda by 2 d dash, that is sine theta, has to be less than equal to 1, which means n lambda has to be less than equal to 2 d dash. And for smallest, n can be smallest 1. So it's a natural number, so it has to be 1, 2, 3, 4. So by this definition, lambda has to be less than, by this definition, lambda has to be less than 2 d dash. So the probing wavelength has to be less than 2 2 times the interplanar spacing for us to see X-ray diffraction. And this is why it necessitates use of X-rays. So in typical crystal structures, the crystal spacing around 3 angstroms. So we use X-rays which of around 1 to 5 angstroms. If we use UV rays, which is around 500 angstroms, so that will be that is unusable for this purpose. So the maximum wavelength we can use is 6 angstroms for an interplanar spacing of 3 angstroms. Then there can be higher order reflections. So we have n lambda equals to 2 d dash sine theta. If we rearrange it, we get lambda equals to 2 d dash by n sine theta. So we define d equals to d dash by n. So any nth order reflection can be treated as a first order reflection from fictitious planes spaced at 1 by n of the previous spacing. So the actual, let's say actual second order reflection is the coming from real crystal planes at distance d dash, but we can create a d equals to d dash by 2 fictitious plane, and we can say that it is a first order reflection from this fictitious plane. So general working form is lambda equals to 2d sine theta. So X-ray diffraction comes from your wave mechanics, which tells us your diffraction interference, and crystal geometry, which gives us the scattering, coherent scattering, and then Bragg's law, which gives us the conditions for peaks. Now, how it is actually how X-ray diffraction is actually happening. So Bragg's law elegantly describes diffraction as a scalar equation based on two parallel planes. However, the real diffraction is three-dimensional vector phenomenon. Individual atoms scatter X-rays in all directions. To truly map crystal structures, we must visualize diffraction geometrically. So you have real crystal lattice where with real cell vectors A, B, and C, and the volume is then given as V equals to A into B cross C. From this we can construct a reciprocal space which has cell vectors A star, B star, C star, and they are given as A star equals to 1 by VC B cross C, 1 by VC C cross A, 1 by VC A cross B. and and then we can define any G vector in the reciprocal space as G HKL, which is given as 1 by mod R, where R is your real lattice vector, which is given as 1 by DHKL, where DHKL is the physical distance between planes in the real crystal. So a plane in real crystal can transform into a single vector in the reciprocal space. So smaller atomic spacing will create larger reciprocal distances. Now, how the scattering is happens? So when an incident X-ray beam hits a single row of atoms, which is given as a vector A1, constructor interference can only happen at specified path differences, which is given as S minus S naught dot A1 equals to H lambda. So this results in a conical shape. This path difference condition creates a continuous cone of maximum energy radiating around the row of atoms. And when we go to two dimensions, where we have two, two A1 and A2, then we get two cones. And this second series of cones intersects with the first, and it creates lines of maximum intensity. And when we go to three dimension, then a third series of cones comes into picture, and it interacts with the first two cones, and it results in single points of maximum intensity. And these common intersections are the points in the reciprocal lattice. So then we come to Ewald sphere, which is a geometric construct to visualize Bragg's law in a reciprocal space. So the radius of Ewald sphere is exactly 1 by lambda. So it depends on your X-ray wavelength. And the center is your crystal sample. And the surface of the Ewald sphere is the zone of constructive interference. So the region where this Ewald sphere will intersect with the scattering cones are the points where the where constructive interference will occur. So diffraction only occurs when a reciprocal lattice point intersects with the surface of the Ewald sphere. So the vector S minus S log by lambda is a diffraction vector, and when its magnitude perfectly matches the reciprocal lattice point, that is r star HKL, which is residing on the sphere surface, that is when Bragg's law is satisfied and a diffracted beam emerges. So, because the reciprocal lattice is tied to the real crystal, rotating the physical sample rotates the entire reciprocal grid, and as the grid turns, new lattice points pass through the surface of the fixed Ewald sphere, which triggers new diffracted beams. So earlier, let's say HKL was 210 and 2 minus 10. Now, if you rotate it, now the lattice points that will be touching, you can say it will be 200 and 1 minus 20. Like these are just representative HKL values. So by rotating your crystal, you can get different planes to intersect with your different planes to result in diffraction. So now the limiting spheres, which means how many planes can we possibly observe. So if we rotate the crystal in all possible orientations at a 360-degree, the Ewald sphere will sweep across the entire reciprocal space, and the limiting sphere is the absolute locus of the farthest points that can ever intersect the Ewald sphere for a given wavelength. So the wavelength effect, molybdenum, copper, or chromium. So radius of Ewald sphere is 1 by lambda. So if we go for chromium, so it has a larger wavelength, that means a smaller radius. So it will capture very limited points. And if we go for copper, which has a medium wavelength, it can go deeper atomic planes. And if we go for molybdenum, which has the shortest wavelength of the three, it will have the largest Ewald sphere, and it can be used to get a vast number of reciprocal points, which it can result in a high resolution structure analysis. So if we want to have the maximum, so if we want to get the maximum amount of reciprocal lattice points for diffraction, you want to go for shorter wavelengths. That means higher atomic number target. So the Ewald sphere tells us the direction of diffracted beams, but the intensity of those beams is dictated by exact positions of atoms within a unit cell. So a simple rearrangement of atoms can eliminate a diffraction reflection completely. So let's compare a base centered and body centered structures. In base centered, ray 1 and 2 scatter the top and bottom planes, and they're out of phase by exactly 1 lambda, which causes concentric interference. But in body centered, the central atom will create an intermediate plane, and the ray hitting this atom is at phase difference exactly half alpha, which is exactly opposite. So this will result in destructive interference, and it will result in zero output intensity. So the same orientation, in one case it gives maximum intensity, in other case it gives zero intensity. So this gives us this gives us diffraction rules for different types of crystal structures. So that so diffraction is used to get convert observable diffraction intensities in reciprocal space to exact atomic positions in real space. So exact atom so intensity of a diffracted beam will be altered by any change in atomic position, and conversely, exact atomic positions can only be determined by meticulously observing these diffraction intensities. So by mapping real space into reciprocal space using the Ewald sphere, we can decode the invisible architecture of materials. So we can so by if we do a complete analysis of X-ray diffraction, we are able to reconstruct the exact crystal lattice. So now I will show you some practice questions. Choose the combination of statements which are true. X-rays are produced by knocking out the inner shell electron from the target material using highly accelerated electron produced with high voltage. X-rays generated from a target has continuous wavelength and also characteristic wavelengths. Heterochromatic radiation, radiation with multiple wavelengths, are used for X-ray diffraction analysis of crystal structures. Continuous wavelength of X-rays is produced due to the deceleration of electrons hitting the target. Which of these are correct? 1, 1, 2, 3, 4, 1, 2, 3, 1, 2, 4, or 1, 2, 1, 3, 4. You can type your answers in chat or you can speak your answer. So the answer to this is C, 1, 2, and 4. So the third statement says that a heterochromic radiation is used for X-ray diffraction analysis of crystal structures, which is false. For X-ray diffraction analysis, we use characteristic wavelengths, which are of particular wavelengths. So this statement is false. Whereas other statements like so knock X-rays are produced by knocking out inertial electrons of target material, which is correct. X-rays generated from target will have both continuous and characteristic wavelength, which is also correct. And continuous wavelength X-rays produced by distillation of electrons hitting the target, which is also correct. Only the third statement is incorrect. An X-ray was produced at the condition of 45 kilovolts and 30 milliampere with copper target. If the intensity of incident X-ray has to be increased to obtain a better intensity of the peak centered diffraction pattern, which among the following condition would you suggest? 50 kilovolt and 40 milliampere nickel target, 55 kilovolt and 30 milliampere cobalt target, 50 kilovolt and 30 milliampere molybdenum target, 45 kilovolt and 30 milliampere germanium target. So now the answer here would be ans- answer here is C. So C, but actually, if you see, we j- if we want to increase the intensity of incident X-rays, then the answer would be C. But because if you put all this in the formula of intensity, that is AIZ V square, then you will see that C has the maximum. C will be the maximum. C will give you maximum intensity, but that formula is applicable for continuous. That formula is applicable for continuous wavelength. That is Bremsstrahlung wavelength. To For diffraction, we don't use Bremsstrahlung. We use characteristic wavelengths, and the intensity formula for characteristic wavelengths is different. And there, if you go for molybdenum, you will have a lower intensity because molybdenum has a very high critical wavelength. Sorry, it has a very high critical energy for characteristic wavelength. So it will actually have a lower intensity of characteristic wavelength. But then when you go for diffraction, since molybdenum has a very small wavelength compared to others, it will result in larger it will result in higher penetration, so it will be absorbed less by your diffraction material, and that will result in a higher intensity in the detector. So this can be solved mathematically. So first you will have to use the formula to get the intensity of the incident characteristic wavelength, which is proportional to your current into your accelerating voltage minus your critical voltage power 1.5. So that will result in the lowest value for molybdenum because molybdenum has the highest critical voltage. So this is the formula for calculating intensity of characteristic wavelength. So which is IK is your intensity of characteristic wavelength, which is proportional to your beam current into V minus Vk power 1.5. Your Vk is your critical voltage for getting that characteristic wavelength. So since molybdenum requires higher energy of critical wavelength, so its critical energy is higher, so it needs so V minus Vk will be lower for molybdenum, and hence it will have the lowest intensity of characteristic wavelength. But you also but when we go for diffraction, then the So diffraction intensity is proportional to 1 by lambda square. So this relation comes from a lot of different parameters, and if you combine both of them, you will get that the molybdenum will result in the highest intensity of the peaks in the diffraction pattern. So just because of its very high atomic number, it is able to get so that so hence it will result in but since it has a very different wavelength from copper, the its its geometry its diffractometer geometry will be different because it will require different angles. So uh, so 50 kV is not exactly required. So you just need above some voltage above your critical wavelength. So critical voltage. So let's say for copper, your critical voltage is around 8 kilovolts. So any voltage above 8 kilovolts will result in your critical wavelength K alpha radiation from copper K alpha radiation. Any voltage above 8 kilovolts. For molybdenum, that voltage is around 20 kilovolts. So molybdenum requires a voltage above 20 kilovolts, but you want high very you want to since but for diffraction you also need very high intensities. So that is why we go for very high acceleration voltages like 40-50 kilovolts. Choose the correct statements about the characteristic wavelength of X-rays. On increasing voltage, wavelength of characteristic X-ray will change. K alpha characteristic wavelength is lower than K beta. There is a critical excitation voltage that produces characteristic X-ray. All of the above. So the correct answer here would be C. So if you increase so the characteristic X-ray wavelength is dependent only on your atomic number of the target. It does not depend on on your acceleration voltage. So if you increase your voltage, your wavelength of characteristic X-ray will not change. So first statement is wrong. Second statement says K alpha characteristic wavelength is lower than K beta, which is also wrong. So K alpha comes from L shell to K shell and K beta comes from M shell to K shell. So M shell to K shell has a higher energy, requires higher energy. So K beta radiation has higher energy than K alpha radiation, which means your K beta wavelength is lower than your K alpha wavelength, not the other way around. And the third point, so we already discussed that to produce characteristic X-ray, we need a critical excitation voltage below which you will not get below which you will not get a characteristic X-rays. So only third point is correct. You are asked by a company to develop a material which will be used as shield for protecting workers from X-ray radiation. Among this, which you would choose? Hint: use mass absorption coefficient concept. Aluminium, lead, magnesium, zinc. So the correct answer for this is lead. So lead has the highest lead has the highest density among these. So it will have very high absorption coefficient. So you would require very less amount of lead, very less thickness of lead to shield. If you use any other material to able to reduce your absorb to able to absorb, you need very large, very thick materials. That is why you for shielding you want to use higher and higher density materials such as lead. A cubic crystal lattice has a d spacing of 1. A cubic crystal lattice has a d spacing of 1.327 angstrom for the HKL plane of 2 to 2. What is the lattice parameter for the unit crystal? 4.596 angstrom, 5.234 angstrom, 4.544 angstrom, 4.999 angstrom. So the answer to this will be 4.596 angstrom. So for cubic crystal lattices, the formula for lattice parameter is given as uh, A equals to D, which is your D spacing, under root of h square plus k square plus L square. So if you use this formula, you will get h square plus k square plus L square, which is 2 to 2 equals to 2 root 3. So you multiply 2 root 3 into 1.327. You get 4.596. Calculate the short wavelength limit for an X-ray beam operating at a voltage of 40,000 volts. 2.5, 0.3, 2.5. So the answer would be actually the options here are wrong. So the answer would be zero point 0.3 angstroms, not nanometer. So the formula lambda SWL equals to 12,400 by V is for calculating lambda in angstroms. So you put here 40,000, you will get 0 0.3. So that will be 0 0.3 angstroms and not 0 0.3 nanometers. Which of the following statements are incorrect? The wavelength of characteristic X-rays does change by changing the operating voltage. The incident intensity of X-ray spectrum will increase with increasing voltage. The intensity of X-ray spectrum will increase with increasing tube current. The threshold voltage limit below which no emission occurs increases with increase in applied voltage. So correct or basically incorrect statements are A and D. So the wavelength of characteristic X-ray does not change when you change the operating voltage, and the threshold wavelength limit below which no emission occurs decreases when you increase the applied voltage and not increase. So this also is incorrect. And intensity of X-ray spectrum increases by increasing voltage as well as tube current. So B and C are correct statements. In a typical XRD spectrum of Fe, that is BCC structure, what is the sequence of peaks observed with respect to 2 theta? 200, 220, 100, 222, 111, 200, 311, 222, 110, 200, 220, 222, 111, 200, 222, 311. So the answer to this will be C. So as we talked about diffraction rules for depending on a lattice structure. So for BCC, the diffraction rules are such that your H plus K plus L should be even. So if your H plus K plus L is even, then only you will get a peak in the diffraction peak. If H plus K plus L is odd, then you won't get any peak. And also the sequence of peaks is such that your H square plus K square plus L square is starts from the lower end. So here, so here 110 will have the minimum H square plus K square plus L square value. So it will be appear first, then 200, then 220, then 222. And in options B and C, yes, H plus K plus L should be even for BCC, and therefore B and D would not be possible because they have 311, 1111, 311. So they will not be possible for BCC. But if you check your A and C, both have H plus K plus L equal. For FCC, HKL should be either even or odd. So all three should be either even or all three should be odd for FCC. So your B and D, they are valid for FCC, because if you see 111 all are odd, 200 all are even, 311 all are odd, 222 all are even. But if you see A or C, then you have 110, which is mix of even and odd. So that is not possible for FCC. They are possible for. So hexagonal cubic packed, there the so there the third indice is irrelevant. Only two indices are valid, H and K, and so it can have all the values for H and K, and L will be determined by negative of H plus K. So if H is 1, K is 1, then L will be -2 and like that. What is the energy in joules of X-ray beams of wavelength 1.789 angstrom, which is your cobalt K alpha? 6.941 into 10 power minus 15, 1.59 into 10 power minus 15, 8.723 into 10 power minus 14, 1.111 into 10 power minus 15. So answer would be D. So you just have to use the formula H equals to H nu, that is Hc by lambda. So if you put all the formula, you will get E equals to 1.11 into 10 power minus 15 joules. Which of the following statements is incorrect? The diffraction pattern coming from X-ray diffraction experiment is the intersection of all the causal planes in 3 dimensions, causal cones in 3 dimensions. Bragg's law is only satisfied by the points lying on Ewald's sphere. In XRD, Ewald's sphere for copper sources will be smaller than for the chromium source. The magnitude of a reciprocal lattice vector is inversely proportional to the distance between adjacent crystal lattice planes. So the correct answer would be C. Copper source has less wavelength. So and reverse sphere radius is 1 by lambda. So copper will have a larger reverse sphere. So C is incorrect answer. Rest of all are correct answers. I mean correct statements. C is the incorrect statement. Which of the following has the lowest K alpha wavelength? Chromium, copper, molybdenum, iron. That is correct. The answer would be C, molybdenum. So by Moss's relation, the element with highest atomic number has shortest K alpha wavelength. So which is molybdenum here. So that are all the questions I had for today. Thank you for attending this session. If you have any doubts, you can ask, or you can, or if you want, you can leave the chat. So that would be correct, but that is not the only role in play. There are different factors affecting the energy of the incident electron. So the statement in what you said is true, but it is not the complete picture. Yes, that has to be. That is how the filter works. So it has to allow k alpha line to pass, but it has to block k beta line. So that is why the absorption edge has to be in the middle. I cannot help with you with assignment questions of this this week, which are I cannot help you with assignments which are active.